Alrighty, good afternoon, lads and ladies. Welcome back to Calc 2. Today we're going to continue our discussion of infinite series by getting a little bit more practice perhaps with limit comparison, but primarily focusing on this new material of alternating series, which is section 11.5. It's a busy day, so we're going to jump right into it. Here we go. All right. We're going to need more paper. We've had the strangest drama going on with these cats lately. There's a neighborhood cat that hangs out outside and was abandoned by someone a while ago. So if anybody wants a cat, let me know. We decided to let him in a second ago just to see how he would get along with our animals, and it was not smooth. So I apologize for any meowing or hissing you hear over the next few minutes. This is MAC2312, section 004. Today is a lecture, and the date is the 25th of March, 2021. As I mentioned earlier, today, we can get more practice with the limit comparison test. But we will primarily be focused on what's called the alternating series test. This is section 11.5. The limit comparison test is the second half of section 11.4. So we talked at pretty good length about the limit comparison test on Tuesday. Hopefully you guys are feeling moderately comfortable with that, but if there is a problem or two that you would like to see from the homework, I would be happy to start class today with one or two such problems. Is there anything like that? Let's plug in us, specifically limit comparison stuff, but anything from the current homework set that you guys want to look at?
I wouldn't mind starting with number 1.
Remember, if you want to look at a particular problem, you can go into the chat and just type, homework 10, problem 7, or whatever.
Number 1.
For anybody who's coming in now, we're just taking homework questions if you want. No, cannot hear you, Cody. All right, now I'm showing you as muted. If you hold the space bar, number 1 on the latest homework, sure.
Yeah, I thought I, what's going on here? Sorry. Great.
Really?
Okay, so you can hear me.
Now I can hear you. Yes, yes, sir.
Okay, I think you were muted then.
Okay.
But yeah, I think number 1's a good start.
All right, let's do it. So we want to know whether this series converges or diverges. Let's take a look. I'm going to label the series as S, and we're summing from 1 to infinity 3 over the square root of n squared plus 2, or something like that. Okay, and I see homework 10 number 7 is the next requested problem, so we'll do these two. At a glance here, so an is 3 over the square root of n squared plus 2, something like that. Remember what we talked about on Tuesday. We're kind of looking for the asymptotic behavior here. So we're looking for sort of the dominant terms upstairs and downstairs. That's what we would want to do to decide how to compare, to gain some intuition about what we think is going on with the series. So the ANs here are 3 over the square root of n squared plus 2. The 3 upstairs is just a constant. It's not growing or decaying. But downstairs, we have the n squared plus 2 under a square root. So kind of, I would say the top is like a constant. It's like 1. And the bottom downstairs, this 2 really isn't relevant. It's the n squared that's kind of the important thing down there. So I would say this is a lot like 1 over the square root of n squared, which is just 1 over n. So if I'm going to do a limit comparison, I want to first pick my bn's. And I would choose here bn to be 1 over n, because I think that's pretty much what an is like. Of course, these are not equal, right? This shaky equal sign here means approximately, and I mean specifically as n goes to infinity, that an is similar to 1 over n. And then I would calculate the number we call c as the limit n goes to infinity an over bn. And then I want to point out again, every time you see me doing this shit, you'll always see me like writing out the formulas before I plug in. I strongly recommend you do the same, not just to keep things square in your head, but also it'll help me give you partial credit on problems if you happen to make a mistake. So by writing this and writing this explicitly, I know that you know what you're doing. So on a test, it would be wise. Not necessary, but wise. And now we're going to actually plug these things in and crunch the limit. So my an is 3 over the square root of n squared plus 2. And I'll put that in parens. And then downstairs I have my bn, which is 1 over n. I'll put that in parens also, just healthy notation. Because you've got fractions within fractions here, it's always nice to say what's the big top, what's the big bottom. The way we evaluate this limit, just do the dot dot dots here, I can run it off to the side, is lim n to infinity 3 over the square root of n squared plus 2 times n over 1. All right, this is just how algebra works. When you divide one fraction by another fraction, that's the top times the reciprocal of the bottom. Whoa, what the fuck? Sorry. The document camera just shit the bed.
It looks like those are saved images of some sort.
There we go. Yeah, it might be taking caps at every so often. Let me see. Looks like this is that also.
Yeah, because that looks like algebra trigonometry stuff.
There we go. Oh, fascinating. Always learning new things I can do with this document camera. All right. Looks like we're back. Yeah, okay. So then from here, I'll multiply the fractions. I get 3n over the square root of n squared plus 2. How do I take this limit?
That's actually where I got stuck. I was able to do everything before taking the limit.
So a few thoughts. As n goes to infinity, the top is going to infinity, and the thing under the square root here is going to infinity. The square root of infinity is infinity. So this is like infinity over infinity. One option would be to try L'Hopital's rule. But I don't recommend it, because L'Hopital's rule is going to involve differentiating this thing down here, which is going to be a little nasty. right? You need the chain rule to differentiate the bottom. You could do it that way, but there's a better way. We have a name for this. We're going to use our renormalization trick. And the idea is that downstairs, I have an n squared under a square root. Upstairs, I have an n. So I'd say that the top and bottom are both growing at the speed of n. So we renormalize by dividing top and bottom by n. And this, the name for this trick is the renormalization trick. I steal that term from physics. It's a physics term where they divide out everything by the speed of light. Useful trick. And it works here as well. So upstairs, this 1 over n is going to hit the 3. I'll just get, it's going to hit the 3n and I'll just get 3. Downstairs, in order to get this guy inside, I'm going to think of him as the square root of 1 over n squared, like this. So again, just an algebra trick. It's a trick that's supposed to be taught in section 2.6 in Calc 1, but I think not everybody gets to see it. So yeah, common trick. When you need to combine something that's not in a square root with something that is in a square root and the things are being multiplied, just take the thing that's not in the square root and write it as the square root of that thing squared. That allows you to put them together because now they're 1 square root times another square root. So these guys can talk to each other. This will give me lim n to infinity. 3n times 1 over n is just 3. And downstairs now I'll have a single large square root. Inside will be n squared plus 2 times 1 over n squared. So sneaky algebra trick. Distributing the 1 over n squared, I get lim n to infinity 3 divided by the square root of n squared times 1 over n squared is 1, plus 2 times 1 over n squared is 2 over n squared. And as n goes to infinity, this 2 over n squared, this is the purpose of the renormalization trick, is that all the pieces that were going to infinity will now go to some constant, and all the pieces that were constant will now go to 0. So this 2 over n squared is going to go to 0. So I get 3 over the square root of 1 plus 0, which is just 3 over the square root of 1, which is just 3. It's the square root of 1 is 1. Okay, so question, what do we learn from this? I want you guys to help me out with the next step here.
We just learned that 1 over n and the original problem have the same either convergence or divergence.
Very good. So my third step here, I'd say since C is positive and finite, we learn that my original series S and sigma n from 1 to infinity 1 over n converge or diverge together. Right? They do the same thing, just as Ethan said. Therefore, say moreover, sigma n from 1 to infinity 1 over n is a divergent p-series. Thus, and I guess we should say here why, because P is equal to 1, which is not strictly bigger than 1. Thus, S diverges also. So this is the sort of structure of any limit comparison problem. First, you have to choose your BNs, and that's usually done with this trick up here where we kind of just ignore all the non-important terms, or the terms that are not the fastest growing. So the top here is a constant. Okay, that grows at the speed of 1, just doesn't grow. The bottom is the square root of a quadratic, which means it's growing at about the speed of n. That tells us how to pick our BNs. And from there, we calculate the limit. If this limit comes out to 0 or infinity, then we're boned. We got to go back and start over with a different BN. But if this limit comes out to a positive, namely non-zero number that is also finite, less than infinity, then we can say, okay, since C is positive and finite, these two series, sigma AN, my series S, and sigma BN, sigma 1 over n, do the same thing. They converge or diverge together. And then finally, we have to say what sigma BN does. So here, sigma BN is the harmonic series. We know this guy diverges. We've proven that and used it 1,000 times. The fastest way to say that is just to say it's a P series with P equals 1. And then finally, you got to finish the problem. Remember what the problem says. Problem says, tell me whether S converges or diverges. So you got to make sure you write something down that says therefore or thus S diverges.
Professor, I have a question.
Sure.
Okay, so we went through all the trouble to find out that the series ends up being 3, but we know that 1 over n is part of the harmonic series and is divergent on step 2. So knowing that it's divergent from there, isn't it more simple to just say that the whole thing diverges in that step?
What was the very first thing you said there? I want to make sure I heard you correctly.
Okay, when you are calculating to see an over bn, finding the limit, right?
Mhm.
You get a positive number.
Mhm.
Why would you go through all that trouble if you know that on step 2, 1 over n, it's a divergent series? And if an and bn, one of them is either convergent or divergent, both of them diverge or converge.
Well, so you have to ask yourself, why does 1 over sigma 1 over n diverging tell me anything about the series I started with? See, step 2, this is the step that connects my series to this series. It's the fact that the an over bn goes to 3 that tells me that my series S does the same thing as the series sigma bn. This right here, all this work is what tells you that the series you started with does the same thing as sigma bn. So this really is the crucial step. See, I know sigma 1 over n diverges, but I don't know whether my series converges or diverges. Right? At the start here, I have no idea whether this converges or diverges. From this, I think it probably diverges. But step 2 is what actually tells me that my series does the same thing as sigma bn.
So in step 2, you are proving the asymptotic behavior for
Right. Right, exactly. So we're comparing sigma n from 1 to infinity, 3 over square root n squared plus 2 with sigma n from 1 to infinity 1 over n. And step 2 is precisely what tells us that this thing does the same as this thing. This gives me that hunch, but we need to prove it, right? This is not a proof in any sense. This is just how I guess what to use for bn. But it's step 2 that verifies that an and bn, just as you said, have the same asymptotic behavior. Only then can I conclude that they do the same thing. If I knew out of the gate that they do the same thing, then sure, I would just say sigma 1 over n diverges, therefore my series diverges. But without computing the limit, I can't say that those two series do the same thing. So this is the work that shows me that these series really are related in the sense that I suspect they are. Does that make sense?
So when you're proving on step number 2 and you get 0, at that point you realize that Bn, or you might have chosen a wrong Bn. And that's how you not do
Yes.
it with a different value, a different Bn.
Precisely. Yeah. And that's what we're saying, right? So it's possible to fuck this up. It's possible to like pick the wrong Bn. And if you chose the wrong Bn, then these two series might not do the same thing. This step is what checks that those two series do the same thing. And if this came out to a number that is not positive or not finite, precisely as you said, it would mean we chose the wrong value for Bn. Does that feel comfy?
Yeah, let's keep going.
Cool. All right. So there are a few other problems we wanted to talk about. I saw in the chat there. Let's address those. I think the next one was number 7.
Yeah, I think Tyler asked for number 7 and Lydia asked for number 12.
All right. I think we probably have time to do both of these. Yeah, 7 is fun. And then let me see 12. Sure. All right. So we're summing 10, 7. We want to investigate the convergence of the series S equals sigma n from 3 to infinity 2 over n to the 1 plus 1 over n. This is a funky looking series because you've got n raised to a weird power that itself involves n. And you'll see this in a handful of problems like n to the n, that sort of thing does show up from time to time. Thankfully, this is not as hard to deal with as that. So again, at the start, I'm just going to look at my ANs. And in this instance, I think it's useful to use some algebra, right? This is a funky looking thing, n to the 1 plus 1 over n. That's definitely what makes this problem feel weird. So let's try to get rid of that. By your rules for exponents, that's the same as n to the 1 times n to the 1 over n. Agreed? So the rule here is the algebra rule. That a to the x times a to the y is the same as a to the x plus y. So n to the 1 plus 1 over n is the same as n to the 1 times n to the 1 over n. It's the algebra rule that we're using in the background there. Now here, there is something sneaky hiding. What is the asymptotic behavior of n to the 1 over n?
It goes to 0.
Well, there's lots of reasonable guesses here, and 0 is among the reasonable guesses, but it turns out to not be correct. N itself is getting very large, right? And 1 over n, which is the exponent here, is getting very small. So if you take a big fucking number and you raise it to a little itty bitty power, the results can be quite interesting. I would say perhaps something like this. Recall that infinity to the 0 is an indeterminate power. So this n to the 1 over n piece is the weird guy. Now I'm going to ask you to dig way back in your memories to a lab before spring break, when we had talked about sequences a little bit, I gave you a couple special limits that I told you I wanted you to prove and remember, specifically involving indeterminate powers. There were
Isn't
two of
that equal to E?
It's the other one. It's the other special indeterminate power limit. So again, recall two special limits. Indeterminate power limits. One of them does involve E. I'll write that one first. If you add 1 plus a over n all to the power of bn, and you send n to infinity in that expression, this will give you e to the a times b. You should remember this forever and ever. There will be a problem on the exam that requires you to use a limit of this form, and knowing this will make it faster. You can use this freely without proof. To cook this up takes a lot of time, right? You look at the natural log of this thing instead of this thing, you bring down the power, you rewrite it as a ratio, you apply L'Hopital's rule, and then you exponentiate. It's a long process. Another special limit of this nature is the nth root of n, which BT dubs is the same thing as n to the 1 over n. This guy comes out to 1. Same process. You take natural logs, bring down the power, apply L'Hopital's rule, and then exponentiate. But both of these take quite a while to figure out. Right? Neither of these come quickly. If you haven't proven the first one, I'll say here, prove one on your own. Strongly suggest you do this. Prove and remember. I can't say it more clearly, right? There will be a point on exam 2 where you need this limit straight up. If you have to cook it up from scratch, it will take forever. Prove this once and you'll actually remember it forever. All right, I'll show you the proof of 2. And you can kind of use this to guide your proof of 1 if you've forgotten a little bit of the L'Hopital stuff. So if an is equal to n to the 1 over n, then the natural log of an is equal to the natural log of n to the 1 over n, which is 1 over n times the natural log of n. So as with all indeterminate powers, the game is to take the natural log and attack that thing instead. So I'll look now at lim n to infinity natural log of an, which is lim n to infinity 1 over n times the natural log of n, which at a glance, as n gets larger and larger and larger, what does 1 over n do?
It goes to 0.
Good. And the natural log of n?
It goes to infinity.
Good.
So it's indeterminate.
Good. Particularly, it's an indeterminate product.
Which means L'Hopital's rule should be applied here.
Not here. So it means we're almost there, right? To handle indeterminate powers, you first transform them to indeterminate products, but L'Hopital's rule can only be applied to indeterminate ratios. So in order to employ L'Hopital's rule, I need to do one little more algebra step. I need to write this as a fraction where the top and bottom are either both going to 0 or both going to infinity. The easiest way to do that here is to just rewrite it like this. All right, if you multiply these two things, you get natural log of n times 1 over n. And now this looks like infinity over infinity, which is an indeterminate ratio. And these are what we want. These things we can L'Hopital. And in so doing, we get lim n to infinity, 1 over n, the derivative of natural log n, divided by 1, the derivative of n. And this goes to 0 over 1, which is just 0. Now, since the ln of an goes to 0, we know an itself goes to e to the 0, which is 1. So the limit as n goes to infinity of the nth root of n is 1. And again, I strongly recommend that you just remember these guys. How do you remember them? Prove them. All right, you want to make something yours in mathematics, prove it on your own. So if you go through the proofs of each of these, you'll remember them. And you are free to use these without proof on the exam. So if you bump into a limit like this on the test, you can just tell me it's 1. If you bump into a limit like this on the test, with like a 2 here and a -1 here, you can tell me that's e to the -2, both without proof. Very powerful, very useful time savers. How do you remember them? Prove them for yourself. So all of this is kind of a diversion from the original problem, right? Why were we looking at this shit? We were looking at this shit because, I'll hold here just for a second. If you want a screenshot of this little diversion, go ahead and grab one. 5, 4, 3, 2. All right. All of this was to try and help us understand better the asymptotic behavior of my ANs. So this AN is asymptotically like 2, I should actually say down here. Fresh page. All of this is to try and suss out the asymptotic behavior. Since n to the 1 over n goes to 1, as n goes to infinity, I would say that this an, which is 2 over n times n to the 1 over n, is a constant divided by, this piece goes to 1, so I would just say it's asymptotically like 1 over n times 1, or just 1 over n. So again, the thing against which we will compare is the 1 over n series, the harmonic series. Is everybody understanding this? This piece right here goes to 1. So as n gets bigger and bigger, he contributes less and less. So I don't really care about him. So this thing is really just like a constant over n. That's what the asymptotic behavior is like. So now I'm going to run my limit comparison test. Based on everything we just said, I believe I should pick Bn to be 1 over n again. And then we will calculate, calculate the limit as n goes to infinity of an over Bn, which in this case would be the limit as n goes to infinity of 2 divided by, I'll write it like this, n times n to the 1 over n, all divided by 1 over n. And that is equal to the limit as n goes to infinity of 2n over n times n to the 1 over n. I'm bringing this 1 over n upstairs as its reciprocal. and multiplying with this. Of course, the ends here will cancel. So out of the way, the ends here will cancel. And that leaves me with then n to infinity, 2 divided by n to the 1 over n. And here's another place where I can use that special limit. I know that this bottom piece is going to 1, so I'll say this is just 2 over 1, which is 2. And we can say here, by our special limit, if we want to make clear where this is coming from. So now I say since c equals 2 is positive and finite, we learn that S and sigma n from, I guess technically from 3 to infinity, 1 over n, converge or diverge together. And then finally, since sigma n from 3 to infinity, 1 over n is a divergent p-series, p is equal to 1, which is not bigger than 1, S must also diverge. That's the job. This is a reasonably quick proof if you know what to do, right? The actual solution of the problem is all right here. But we had that long side discussion all about these special limits. And those special limits are things that you really do want, right? On an exam, I wouldn't have any issue writing this. I can write this in 5 minutes, quick problem. But if I have to go off to the side and spend all that time worrying about what this piece does, then that's a 20-minute problem. So make sure you remember these important pieces. Those two special limits, this guy and the e to the ab limit, are both really, really useful tools. You want to hold on to those. Say it one more time. The way to remember those is to prove them for yourself. Don't take my proof and go, okay, I remember. Spend the time, get on a whiteboard, work with it until you understand it. Questions on this guy? Okay, there was one more that we wanted to look at, number 12. I can look at this quickly. 4n plus 7 to the n over 4n plus 6 to the n. Can I cancel the 4n's? Where was my series starting? 1 to infinity. Okay, first question, important. Can I cancel the 4n's?
No.
No, good, thank you. Ethan, Matthew, I appreciate that, Ariel. 4n is not a factor of the top, right? I cannot factor a 4n out from this, nor can I factor a 4n out from this. So we certainly cannot cancel those. However, if I'm looking at this series and asking, who really matters here? Who grows faster, 4n or 7 to the n?
7 to the n over 6 to the n.
Right, 7 to the n dominates 4n big time. This is a linear growth, right? It's a polynomial of degree 1. This is exponential growth. And we remember from as far back as college algebra that exponentials trounce linear functions. Even if this was a 4n to the 10 or a 4n to the million, 7 to the n would win. Exponentials always trounce polynomials. One possible avenue for solving this problem is to use a limit comparison test. That's why it shows up here. And Cody correctly identified the choice of Bn as 7 to the n over 6 to the n. Is there any other avenue towards a solution here? Is there anything else we see about these ANs observing that they are asymptotically 7 to the n over 6 to the n, which would be 7/6 to the n. That might be manageable here.
It's a geometric, so 7 over 6 is greater than 1, so it diverges.
It's true that if I were to run a limit comparison test against this guy with this guy as Bn, then sigma Bn would be a divergent geometric series. That's true. That's certainly true. And that's how we would solve this using the limit comparison test. If I wanted to solve this with the limit comparison test, I would pick Bn to be 7/6 to the n, calculate the limit of An over Bn. That limit would come out to 1. And we would then conclude that the series S diverges because the series sigma 7/6 to the n is a divergent geometric series. What else do you know, though, about 7/6 to the n? How bad is the divergence? Is it like 1 over n? Or is it worse? If you plug bigger and bigger numbers in for n, does 7/6 to the n go to 0?
No.
No, yeah, it does not. It goes to infinity. So I suggest the test for obvious divergence. It will be faster. Remember what TFOD says. It says if the limit of the ANs is non-zero, then sigma AN diverges. Here, the limit of the ANs is the limit as n goes to infinity of 4n plus 7 to the n over 4n plus 6 to the n. And at a glance, the top and bottom are definitely both going to infinity. So I have an indeterminate ratio, which is something I can apply L'Hopital's rule to. The derivative of 4n is 4, plus the derivative of 7 to the n is 7 to the n times the natural log of 7. And downstairs, I get 4 plus 6 to the n times the natural log of 6. This is coming from a differentiation formula that we saw on Tuesday also, that b to the x primed is b to the x times the natural log of b. Now this still looks like infinity over infinity. because 7 to the n and 6 to the n both go to infinity. But if I apply L'Hopital's rule one more time, the 4s go away. I'll get 7 to the n. Remember, natural log of 7 is a constant. So I'll just get another copy of ln 7. And this is lim n to infinity 7 to the n over 6 to the n times this constant over here, which I'll just write as ln 7 over ln 6 all squared. Again, this is constant. And the rest is lim n to infinity 7/6 to the n. So this constant is here. What does 7/6 to the n do as n gets bigger and bigger?
Goes to infinity,
Yeah,
as
remember
it's a
this is-
geometric, sorry.
Good, yeah, exactly. It's a geometric sequence. 7/6 to the n is a geometric sequence. So this is equal to infinity times log 7 over log 6 all squared. And since this is just a constant, this is infinity. So not only does this series diverge, it diverges like wildly. It diverges really rapidly. The terms don't even go to 0. So S diverges, right? I say infinity is not equal to 0. So S diverges by TFOD. This is the nice solution here. You can do it using the limit comparison test also, right? That will work just fine. But the limit work in the limit comparison test is going to be a little bit tricky. You just have to be careful with your algebra. It will come out nicely, but you'll end up needing some L'Hopital's rule there as well. And the fun game is anytime you have a series where the general term, the ANs, don't go to 0, TFOD will get the job done, and TFOD is simpler. So we often prefer this if it's doable. Questions on this? Okay then. Let me bring my feedback here. I think that's enough work with homework problems. So let's shift to the new material. The next section of the book is 11.5, which is on alternating series. It's a new convergence test called the alternating series test, and it comes with an estimation theorem. And this is the only estimation theorem that I'm going to require you to learn. AST itself is very easy to run. I'll prove it for you. In fact, the proof is pretty nice. But then beyond telling you whether a series converges or diverges, this section also comes with a tool for telling you the value of the series, or at least approximating the value of the series. Beyond just like, crunching out partial sums. Gives you a quantitative measure of the error. Here's the test. Well, I guess first we need to talk about what an alternating series is. Let's do that. A series is called alternating if every other term changes sign. So these are series that look like A0 minus A1 plus A2 minus A3 plus A4 minus, and so on. Or maybe minus A0 plus A1 minus A2 plus A3 minus A4, and so on. We need some notation, and it's nice to have notation that is slightly different than what we're used to. So usually these will be written as sigma -1 to the n times bn, or sigma -1 to the n plus 1 times bn. There's other ways to get the alternating behavior, but the big thing is we call the positive part of the sum end. A little more vocabulary here. The thing inside the sum, the thing that's being added up, whatever's inside the sigma, is called the summand. So the positive part of the summand we call Bn. These could start at 0, or could start at 1, or could start wherever. So I'm not specifying the starting value for the index here. It's the -1 to the n. It's the power of -1, which makes these alternate. Because -1 to the 0 is 1. -1 to the 1 is -1. -1 to the 2 is 1. -1 to the 3 is -1, and so on. A quick comment, there's other ways this shit can happen. Also possible. What's the cosine of 0? Good, 1. What's the cosine of pi? Excellent, -1. The cosine of 2 pi? It's +1 again. Not 0, +1. Sine of 2 pi is 0. The cos of 3 pi? -1 again. So -1 to the n is actually equal to cosine of n pi for all integers n. Just something to be on the lookout for. So you don't always have a power of -1. You could have something like cos n pi. And there are sneaky ways to do this with the sine function as well. What's going on with the cosine function here is that every time we go up by pi, we're going from the left side of the unit circle to the right side, to the left side, to the right side, to the left side, to the right side. If you wanted to do this with sine, you'd have to go from the top to the bottom, to the top, to the bottom, to the top, to the bottom. That would require integer multiples of pi over 2, or odd integer multiples of pi over 2. Another thing to be aware of, just because you have a -1 to the n, or a sine or a cosine, doesn't mean, I should say that more carefully. Just because you have a power of -1 or a sine or a cosine doesn't mean you're alternating. -1 to the 2n, since 2n is always even, doesn't alternate. Sine of n or cosine of n on their own don't alternate. So just be aware of that. If you want to check whether a series is alternating, you should just write it out and make sure that every term really does change sign. All right, so that's what an alternating series is. A concrete example. This is an alternating series. The first term here is -1 squared over 1. And then the next term is -1 cubed over 2. And then the next term is -1 to the 4 over 3. And then -1 to the 5 over 4, and so on, which is 1 minus 1/2 plus 1/3 minus 1/4, and so on. This is an alternating series. Here, Bn is just 1 over n. It's the positive part of the sum n's, right? So the -1 to the n plus 1 is what makes us alternate. And everything else inside here is 1 over n. And if you look at this written out and just ignore the plus minus, it's 1 over n, right? 1, 1/2, 1/3, 1/4, that's 1 over n. Okay. Let me show you the alternating series test now. I'll give you a second to write. Again, Bones, watch your face, Bubba. I don't want to hit you with the chair. Okay. If you need a screen cap, go ahead and take one. Turning the page in 5. So we're going to have two theorems here. The first is just the alternating series test. It's a convergence test. Says if S equals sigma -1 to the n times Bn, or sigma -1 to the n plus 1 times Bn, or whatever, is an alternating series with positive parts Bn, then S will converge provided two things are true. First, the sequence Bn is decreasing. So this kind of sucks, right? This is kind of like the integral test. We know that showing something is decreasing can be a little bit tricky. The other thing that we need in conjunction with this to guarantee that the series will converge is that the Bn's themselves go to 0. So that's it. That's the theorem. If S is an alternating series, however you want to write it, -1 to the n bn, -1 to the n plus 1 bn, cos n pi times bn, whatever, is an alternating series of positive parts bn, then you can be sure that the series will converge if these two things are true. I want to make a little note about this guy. WebAssign uses the following definition of decreasing. They say bn plus 1 has to be less than bn for all n. This works. It's certainly true if the next term after any given term is smaller than the given term, and that's true for every number n, then your sequence is a decreasing sequence. All right, so bn and bn plus 1 are two generic terms of the sequence bn, one immediately after the other. If the next guy is always smaller than the previous guy, that's precisely what it means to be decreasing. And this is fine, but this is sometimes hard to prove. And you cannot just check one or two values for n and say this is true. If you want to use this, you must prove that bn plus 1 is less than bn for all n. Not just check a few values. It's possible that b2 is smaller than b1 and b3 is smaller than b2, but then maybe b4 is bigger than b3. Checking that the first few terms follow this pattern is not sufficient to show that the sequence is decreasing. And WebAssign will contradict me on this. I'm telling you the rule for this class. You can't just check that this is true for one or two values of n and call it a day. That's not sufficient. It's entirely possible that a sequence starts off decreasing, but then turns around and does all sorts of fuck shit. That's not what we're interested in. As you go through the little help things in WebAssign, it will ask you to verify this inequality for a few values of n and then call it a day. That's not good enough on a test. Sometimes proving this inequality isn't hard, and I'll show you an example where I prove that directly. And if it's easy to do, go ahead. But smarter paths to prove bn is decreasing? Include the derivative. Or argue that bn is the reciprocal of an increasing sequence. Just like for the integral test. I suppose I should be putting this bn in curly braces. And because I know someone's going to beat me to it if I don't say it, we can inject a word here. What's the word that goes here?
Eventually.
Eventually. Good. So the sequence bn may not decrease right away. If the first few terms of bn are not decreasing, but then from some point on it is decreasing, that's good enough. Because remember, the tail is what determines convergence. I don't care what the first few terms of any series do. I don't care what the first finitely many terms of any series do. The first 10 billion terms may not be decreasing, but if from 10 billion on, the sequence Bn is decreasing, then we're good. So of course, down here, you can inject eventually as well, right? Okay. Let's use the theorem. I'll hold for a second in case anybody's writing. Any questions on the statement of the theorem or these comments about decreasingness? Ooh, I just had something I thought of. What did I want to say? Not that. Oh yeah. If a series fails the alternating series test, we learn nothing. Just because a series doesn't satisfy both 1 and 2 above does not mean the series diverges. So it's kind of like the TFOD in this sense, right? Like the negative result here is inconclusive. AST can never tell you that a series diverges. It either tells you that a series converges or it tells you nothing. There are some ways you can think about the implications, specifically if it fails the second condition, if the BNs don't go to 0, that does imply that the original series fails TFOD. And usually it will be this one that fails. But I just want to say that the negative result for the alternating series test is inconclusive, not diverges. You cannot ever tell me a series diverges by the alternating series test. The alternating series test doesn't have the power to say a series diverges. It either says the series converges or it tells us nothing. All right. How am I doing on time? Almost there. So let's look at that example from earlier. We observed previously that this is an alternating series. Notice that it'll get right through TFOD and that none of our other tests apply. Because the limit as n goes to infinity here of the ANs is the limit as n goes to infinity of -1 to the n plus 1 over n. This is 0. It requires the squeeze theorem. But it does pass. The top is bounded. The bottom goes to infinity. So this TFOD doesn't teach us anything. The other thing I want to comment here the integral test and comparison tests can't be used here because an is -1 to the n plus 1 over n is not positive. All right, remember all of our tests so far, the integral test requires that the corresponding function be positive. Here, the corresponding function is really nasty. It's definitely not positive. And the comparison tests both require that the series have positive terms. The direct comparison test says you've got to be bigger than 0 and smaller than something else. And that the limit comparison test says, an and bn have to be positive terms. So none of the tests that we've learned so far actually apply to this series. So we need a new test. This is a series we could not possibly handle with our other tests. But the alternating series test is really easy with this. S equals sigma n from 1 to infinity, -1 to the n plus 1 times 1 over n. So S is alternating. And the bn's here are just 1 over n. So we check the two items. One, is the sequence bn decreasing? Well, here is a case where it's easy to use the inequality. Is bn plus 1 always less than bn? This would be equivalent to saying 1 over n plus 1 is less than 1 over n. It's important you understand what bn plus 1 is. It's like f of n plus 1. It's what you get when you swap n for n plus 1 here. Is everybody comfy on why bn plus 1 is 1 over n plus 1? It's not 1 over n plus 1 like this. Very different. Okay. So the inequality we need to prove to show that bn is decreasing is this inequality. When I just plug in my bn's, I get this. 1 over n plus 1 is strictly less than 1 over n. Is that true? Well, I can work with this inequality now and try to reduce it to something I know to be true. Specifically, I can cross multiply. So I get n is less than n plus 1. All right, I'm cross multiplying here by n and n plus 1. And then if I subtract n from both sides, this reduces to the inequality 0 is less than 1. So what I've shown here is that bn plus 1 is less than bn if and only if 0 is less than 1. Since 0 is indeed less than 1, it follows that bn plus 1 is less than bn. And this is true for all n. Yes. Questions on the inequality work here? This is how you prove an inequality of this form. You take the inequality you're trying to prove, you write it down, and then you reduce it to something which you know to be true. If you can simplify your inequality to a true statement, then your original inequality is true. This is not always easy. Sometimes this is incredibly hard. But our first condition is satisfied. Second condition is lim n to infinity bn equal to 0. Well, the limit as n goes to infinity of the bn's here is limit n to infinity 1 over n, and that is 0. Yes. Therefore, by the alternating series test, S converges. All right, easy peasy lemon squeezy. Not too bad. It's all just about showing these two things. If you can show these two things, then your series converges. Only works for alternating series. And I want you to notice that this is a really lax condition. Right? In general, if the terms of a series are decreasing and go to 0, that does not guarantee that the series converges. If you take out this alternating piece, sigma 1 over n is the divergent p series. So it's much easier for an alternating series to converge than a series with positive terms. The reason for that is in the proof. The proof, along with the estimation theorem, I am going to show you in the lab. So we are at the end of the lecture period. We're going to take about 15 minutes. Grab yourself a snack, relax for a second, then we're going to come back and I will show you the rest of 11.5. It's very important, so please, you got to stick around. But we can take a few minutes break. I'll see you guys back here at 2 o'clock. Alrighty, gang, we're going to be coming back here in just about 1 minute. So if you could gather yourselves back at your computers or whatever device you're using. I'm going to flip the screen share back on in just about a minute here. I got to use the bathroom and then we're going to get started. Alrighty, gang, we are going to get started with our lab. Today, lab is just going to be a continuation of the lecture because I want to share with you guys the second half of the alternating series test. It's really its own theorem. So without further ado, here we go. This theorem has its own name. It's called the estimation theorem. Sorry, my dog is drinking, it's loud. Estimation theorem or alternating series. And like the alternating series test, it only applies to series which alternate. An estimation theorem, and there are several of these in your textbook, is a theorem that allows us to quantitatively estimate the sum of a series. So no doubt, you've noticed that most series, we have no idea what they add up to. The so-called sum of the series is very hard to discern from the terms. We can always look at the partial sums, but it's very hard to say in most cases how far off the partial sum is from the actual series itself, from the full value of the series. With the exception of geometric series and telescoping series, we can't do this. Now we have something that will help us in the slightly more general case of alternating series. So I'm going to state the theorem for you. We'll talk a little bit about what it means, and then we'll look at some examples. The theorem says if S is a convergent alternating series, then the difference between the value of the full sum of the series S, remember S stands for the whole series, and the nth partial sum S sub n does not exceed, is less than or equal to B sub n plus 1. Where the bn's, again, are the positive parts of the summands of the series. The proof is pretty nifty. Let me draw for us here a number line. Remember that S, here, S would be something like B0 minus B1 plus B2 minus B3 plus B4, and so on. And Sn, the nth partial sum, would be like B0 minus B1 plus B2 minus, and so on, out to Bn. And this may be positive or negative depending on what capital N is. Suppose B0 lives over here. The first partial sum, S0, is just B0. The next partial sum, S1, is B0 minus B1. So B0 here is also S0. B1 is going to be negative. So we take B0, and then the next term of our series is minus B1. So to go from S0 to S1, we need to subtract B1 from S0. So what we're doing over here is we're moving to the left by B1. Right, because we subtract B1. And then what is S2? S2 is B0 minus B1 plus B2. So to go from S1 to S2, we go to the right. We are adding B2. And since this is a convergent alternating series, we can trust that B2 is smaller than B1. So we're going to walk back to the right some amount. That amount is plus B2. And we can trust that B2 is smaller than B1. So I'm not going to walk past this guy, which lands S2 like right here. But then S3, the third partial sum, would be B0 minus B1 plus B2 minus B3. So if I want to get to S3 on my number line, I need to walk back over the other direction because it's being subtracted, but I'm going to walk less than I did for B2 or for B1 because we're going back the other way. So this is minus B3. And that lands us up here, right here. And that gets us to S3. If you continue this pattern, thinking about what each one of these steps does, every time we look at one further partial sum, we're going to bounce back and forth. But because the BNs are decreasing, each bounce is smaller. So let's say it like this. Because BN is decreasing, each bounce back and forth is smaller than the last. So you end up with this nesting thing. You've got S0, S1, S2, S3. S4 would have to be somewhere in here. And then S5 would have to be somewhere in here. And then S6 somewhere in here. And they have to keep going in and in and in, closer and closer. I'll draw one more of these in. So to get to S4, we would add B4, but we're not allowed to go further than we did from S2 here. We're not allowed to go past this line. So we would be adding B4, and that would make S4 show up right here. So it goes, you start somewhere over here. S is like 0 is somewhere over here. S0, your 0th partial sum, then S1, your next partial sum, then S2, your next partial sum, then S3, then S4. S5 would have to be between S3 and S4. And then S6 would have to be between S4 and S5. So this nesting process leads to a nesting process. Nesting just means one inside the next. Focus. This nesting process forces the partial sums to get to like sort of walk in towards a center. So eventually, after this process continues, you're going to go towards something in the middle there, and that something in the middle would be the limit of the SNs, which is the full infinite series S. And the big deal here is that if you look at the distance from the full value of the series S to any one of the partial sums, let's look at the distance from S to S2. That's this horizontal distance. What we can say for sure is that the distance from S to S2 is smaller than B3. Does that make sense? This distance from S to S2 has to be smaller than B3, because to go from S2 to S3, we jump back over S. So the highlighted distance right now is smaller than this distance, because the distance from S to S2 fits inside the distance from S2 to S3. And the distance from S2 to S3 is B3. And that's precisely the statement. The distance from S to S2 is smaller than B3. And that works no matter what you use for n. Instead of 2, you could use 3 or 4 or 5. This is also how you prove the alternating series test, right? Because these things nest and they have to come towards a center, if you assume that the bn's are decreasing and you assume that they have limit 0, then this nesting process has to walk in and in and in and in until you get to some limit inside. So how do we use this? Again, I want to return to the example we were just looking at. So here's the statement of the theorem. This is the thing that you need to get comfy with. Understanding this picture will help. There's a version of this picture in the book. And of course, in print, it is easier to display fine details like this. So I invite you to look here in the textbook, section 11.5, where they offer the full proof. It's precisely like I was saying, right? You start at 0. To get to S1, you have to add B1. Now, if we assume the bn's are decreasing, then to get from S1 to S2, we subtract B2, but B2 is smaller than B1. To get from S2 to S3, we add B3, but B3 is smaller than B2, so we don't go past this. We got to stay in here. Since B4 is smaller than B3, we're walking back the other way, but we're not walking past this. That's the idea. And so you get this nesting process. And we're getting closer and closer and closer to S with each one. The big deal here is that the distance from any partial sum S, S4, say, to S, is always less than the next step, because S itself is between S4 and S5. And the step to get from S4 to S5 is B5. So the distance from S to S4 has to be less than this pink distance here, B5. And that's precisely what this says. I can try to highlight this here. Like the distance from, let's say, S to S2 is this distance. That distance is the absolute value of S minus S2. We use absolute values for distances here because this could be positive, could be negative. In this case, S2 is larger than S, so that if you subtract those, it would be negative, but we just want to talk about the distance. And then B3 is this distance right here. So this is equal to B3. And you notice that this distance right here is indeed shorter than this distance right here. So the distance from S to S2 is smaller than B3, because to go from S2 to S3, you subtract B3, and B3, that's going to jump you over S. So the distance from here to here is smaller than the distance from here to here. And that distance is B3. And this works regardless of n, not just for n equals 2. This works for n equals 3, or n equals 4, or n equals 5. So how do we use it? Well, it tells us how many terms we need in a partial sum to get a desired accuracy. So an example of a problem we can solve with this, I could say approximate or estimate, either one, approximate the value of, I'll use the same series we've been working with, sigma n from 1 to infinity, -1 to the n plus 1 over n, accurate to 3 decimal places. We know that for large values of n, Sn should be very, very close to S. The question is, what value of n, capital N, do I need in order to get Sn accurate to 3 decimal places? The error, so if we're going to be accurate to 3 decimal places, we can be off, or I'll say we can't, I'll say it like this, we want the error to be less than what? Well, I need zeros in the first 3, right? Because I want the error in the first 3 decimal places to be 0. I want to be accurate to 3 decimal places. And then I'll put a 1 over here. So we can be off by 1 in the 4th decimal place. This could actually give trouble depending on how you're rounding. But this is a safe move here. So we need the first 3 to be exact, and we're allowing it to be off by 1 in the 4th decimal place. If the 3rd decimal place were a 9, and this guy, the 4th decimal place were like a 5, then if you're off by 1 in the 4th and the correct 4th decimal place is a 5, then you would end up rounding the 3rd decimal place up by 1. But ignoring rounding issues, this would definitely suffice. So by the estimation theorem, for alternating series, we know that the distance between the full value of the series and the nth partial sum, this is the error, is less than bn plus 1. We want the error to be small, less than this. And we know that the error is less than bn plus 1. Bn plus 1 is 1 over n plus 1, right? Because bn here is 1 over n. So it suffices to solve the inequality one over n plus 1 is less than 0.0001. So whatever you want your error to be smaller than, you need to set bn plus 1 less than that. Here, bn plus 1 is 1 over n plus 1. So in order to guarantee that my error is smaller than 0.0001, I need to solve the inequality bn is less than 0.0001. And since bn plus 1 is 1 over n plus 1, I set that less than 0.0001. Solving an inequality like this can be tricky, especially since we're only interested in whole number solutions. I'll show you how to do it here. This means 1 over n plus 1 needs to be less than, let's write this as a fraction also. This is 1/10, 100th, 1,000th. This would be 1/10,000. So I need 0.0001 as a fraction. That's 1 over 10,000. Now I can cross multiply to get 10,000 is less than n plus 1, which means that I subtract 1 from both sides, 9,999 is less than n. So any n bigger than 9,999 will work. So again, the procedure here, if you want your series estimated with an error less than any particular number, you need to set bn plus 1 smaller than that number. Then solve for n. What is s? Let's say n's bigger than that. Take n equal to 10,000. S 10,000 is the sum from n equals 1 up to 10,000 of -1 to the n plus 1 over n. This is not something you should compute by hand. This would be horrible to compute by hand. You have to add up 10,000 fractions, all with different denominators. No, thank you. But I can ask my buddy, Wolfram Alpha, to do it. And there we go. So I get 0.693097. Just copy that down. 0.693097, blah, blah, blah. Now, would anybody care to gander the actual value of S here? S is sigma n from 1 to infinity, negative 1 to the n plus 1 over n. I think I mentioned in passing what this was last week. I'm just curious if anyone remembers.
Maybe 2/3. I don't know.
It's not 2/3. It's actually something quite strange. It's the natural log of 2. And I'll be able to prove this for you later. But we'll need to talk about some stuff called power series before we can prove this. So what is the decimal approximation for the natural log of 2? 0.693147. And would you look at that? Our first 3 digits are correct. And the next digit, 693, is that, did I get that right? 693, oh, there's a 1 in here, 693147. Yeah, our next digit is off by 1, which is precisely what we should have, right? Our error should be 0.0001. So we should be off by at most 1 in the 4th decimal, and we are 6930, 6931. Cool shit, right? I'd like to do one more example with this, and then I'll let you guys go. There's no need to push any harder today than is necessary. Let's approximate the series S equals sum from 0 to infinity, negative 1 to the n times 4 over 2n plus 1 to 3 decimals. Oh, I see there's something in chat here. Yeah, it is. This is nifty shit, right? I love this stuff. It's so cool. So the big issue before is that we didn't know how far to go in my partial sum to get 3 decimal places of accuracy. Maybe the first 5 terms is enough. Maybe you need the first 10,000 terms. And the fun of this theorem is it now tells you exactly how far you need to go in your partial sum in order to get any desired level of accuracy. All right. Well, here, first, let's just verify that this converges. We'll use the alternating series test. So S is sigma n from 0 to infinity, negative 1 to the n times 4 over 2n plus 1. That's the same as sigma n from 0 to infinity, negative 1 to the n times 4 over 2n plus 1, like this. So my Bn is 4 over 2n plus 1. It's the non-alternating part of the sum end. Is Bn decreasing? There's a bunch of ways to attack this. Here we could again dive in and do the actual inequality. Bn plus 1 is less than Bn if and only if 4 over 2 times parentheses n plus 1 is less than 4 over 2n plus 1. You can divide both sides by 4. The 4's go away. You get 1 over here. You distribute the 2 over the n plus 1, and you get 2n plus 3 is less than 1 over 2n plus 1. And then you can cross multiply, and you get 2n plus 1 is less than 2n plus 3. And then from here, you've got some choice. You could subtract 1 from both sides. Hopefully this is evident at this point, but you have 2n is less than 2n plus 2. And then you could divide both sides by 2. You get n is less than n plus 1. And then you can subtract n from both sides, and you get 0 is less than 1. So yes, the bn's are decreasing. This inequality is true because it reduces to 0 is less than 1, which is an evidently true statement. Some would argue that you could stop here. I guess if you're smart, at this stage, you would just subtract 2n. I don't know why I didn't see that. Yeah, subtract 2n from both sides, or just 2n plus 1 from both sides, and you immediately get to here. But yes. Yes, it is. And then the limit of the bn's that equal to 0? Well, the limit as n goes to infinity of bn is the limit as n goes to infinity of 4 over 2n plus 1. That's 4 over infinity, which, yeah, is definitely 0. So, yes. Therefore, S converges. If we apply the estimation theorem, we'll see that the absolute value of S minus Sn is less than B sub n plus 1. And we want the absolute value of S minus Sn less than, what do we want? 3 decimal places, right? So 0.0001. So it suffices to solve the n plus 1 is less than 0.0001, which is equivalent to saying 4 over 2 times capital N plus 1 is less than 0.0001. Because this is Bn plus 1. And again, we can distribute downstairs and do all the same sort of inequality things that we would want to do. This is going to be 4 over 2 cap n plus 3 is less than 1 over 10,000 again. If I wanted 2 decimal places, they just lop off a 0. And then we can do all the same sort of things. We'll cross multiply. That'll give me 40,000 is less than 2n plus 3, which means 39,997 is less than 2n. And that would mean that 39997 over 2 is less than n. No, I don't know what that is off the top of my head. It's somewhere around 20,000, but just to be careful, never hurts. 3997 divided by 2. 19,998.5. So we need n greater than 19998.5. So n equals 19999 will work. Oh, do I have an extra 9 here? 19,998. No, that's good. All right. This means that the nth partial sum of this series with n equal to 19,999, so the 19,999th partial sum should be accurate to 3 decimal places. What is that partial sum? Well, that's the sum from n equals 0 up to 19,999 of -1 to the n times 4 over 2n plus 1. This one I haven't talked about. Would anybody care to guess what this is going to be close to? Or what the full series S is going to be equal to? This part's going to be fun. So we're going to come back to Wolfram. Ah. Anybody see it?
Pi?
Yeah, it's pi. So the actual partial sum here, I'll write it down, is 3.1415426 blah blah blah. And the actual value is pi, which is 3.1415. We don't need this. 3.1415926 blah blah blah. And again, we're good to 3 decimal places. 3.1415, 3.1415. The full sum here is actually just pi. And this is one of the early tools for calculating pi. Believe it or not, this is called a Leibniz sum for pi. He discovered it by, you guessed it, power series. And this is what your calculator does when it needs pi, by the way. When your calculator needs a representation of pi, people ask me, like, what is pi? You know, the decimal goes on and on and on forever, so there's no like convenient way to store it. You can't tell a computer, just draw a perfect circle, then divide the diameter or the circumference by the diameter, because a computer doesn't know what the fuck that means. It uses this series. Or a modified version of this series that converges a little faster, so you don't need such a large n value. But yeah, cool shit. So this is how Leibniz would calculate pi, the German mathematician who was partially responsible for the discovery of calculus. You want to know pi to any number of decimals? Just set up this inequality, solve it, and then use that partial sum. It will work. There's cool shit out there like this. There's one for 1 over e. And I would be happy to go through that with you guys, but I don't want to burn you out. I think you've probably had enough for today. So are there any questions grinding through your brains that you'd like to look at before I let you go for the day?
So if we had to do this on a test, how do we calculate that?
On a test, I would just ask you to get to this stage. You got to tell me the n value. So I'd ask, For what value of, or what value of n do you need for the partial sum to have this error or that error? On a test, I would not ask you to do this. The other option would be to give you a series that converged much, much, much faster. Like if we wanted to, a valid exam problem here would be something like a valid exam problem exactly of this nature. Estimate S equals sigma n from 0 to infinity, -1 to the n over n factorial to 2 decimal places. Because here the inequality you would need to solve is 1 over cap n plus 1 factorial is less than 0.001. And this is surprisingly short. This happens pretty quickly. This would be true if and only if 1000 is less than n plus 1 factorial. Now the factorial makes the inequality a little bit hard to solve, but you can check with a few n values. N equals 3 means n plus 1 factorial is 4 factorial is 24. N equals 4 means n plus 1 factorial would be 5 factorial, which is 120. N equals 5 means n plus 1 factorial would be 6 factorial, which is 720. So n equals 6 would do the job. There, n plus 1 factorial would be 7 factorial, which I don't remember off the top of my head. That certainly is larger than that. Yeah, 5040. So this is the first one where we're larger than 1000. So this is true if and only if n is greater than 6. Strictly larger than 6, 7 works. So here the 7th partial sum would do the job. That's still a little bit long. But yeah, on a test, I would just ask you to give me the n value. We could ask you to add this up, but this would be a little bit too long for a test. So yeah, in all likelihood, if this shows up on a test, which it may well do, I would be happy once you got here. I would just ask you for the n value. Does anybody know what this series converges to? So fun questions to investigate. So every time you're given an infinite series to play with, it's worth plugging it into Wolfram and seeing, do I know that thing or not? This guy is actually 1 over e. So this is going to give me the first 2 decimals of not e, but its reciprocal. So, 0 to 7. So 0.36 I'm hoping for here. 0.36. Yeah. All right. So that's where I'll leave it. Other questions here? Anything else that's burning in your brain before I let you guys go today? Alrighty then, I will turn you loose. Please work hard on this homework between now and next Tuesday. Next Tuesday, we're going to talk about the root and ratio tests and the concept of absolute convergence. Having done that, we will be ready for exam 2. So exam 2 will be the week after next. I'll be releasing your study guide late next week, and then we'll be on the road. After exam 2, we're going to talk about power series. After we talk about power series, we're going to talk about those application things that I mentioned in the Discord the other day. And then we'll be done with the semester. You'll be done with Calc 2. So we're getting there. We really are. Exam 2 tends to be tough. And the power series part of exam 3 tends to be tough. So again, you really need to invest that time now. I promise you it will pay off. It's a good question. Is there an alternating series for the golden ratio? Maybe. Probably. I'm not sure. Yeah, I mean, there's likely many different infinite series representations for the golden ratio. But is there a clean one? I know a way to get the golden ratio out as coefficients of a power series using what's called a generating function. But I'm not aware of a nice one, at least not on the top of my head. So that could be a fun project to try and find such a thing. But yeah, I'm not aware of one, at least not off the top of my head. Here is, yeah, this is an alternating series. So here is an alternating series for the golden ratio. It's a little bit gnarly. You've got this 13/8 out front, and then you've got your -1 to the n plus 1. That's going to make it alternate. 2n plus 1 factorial divided by 4 to the 2n plus 3 times n factorial times n plus 2 factorial. Fascinating little series here. I bet this converges quite quickly. But yeah, that is new to me. So cool question. And there is an answer on the wiki page for golden ratio. Any other questions we would like to look at? Alrighty then, I'm going to turn you guys loose. I hope you have a lovely rest of your week. If you do want to talk about anything, as always, you can come see me in office hours or send me a message on Canvas. Make sure you're working hard on this homework, really working on it, struggling. Let yourself struggle. Struggle is good. And then share your results with other people. Make sure you can communicate them as well as arrive at them. As always, you can reach out to me through any of the normal channels. Otherwise, I'll see you guys on Tuesday.
Have a great day, Professor. See you later.
Thank you.
Take care, guys.